All right. Ending up this unit, we are going to do and learn a little bit about this guy right here. He's the big kahuna. Big kahuna right here. I mean, when it comes to scientists, he might have been the most intelligent scientist in the history of scientists. In fact, a lot of people think that they didn't measure IQ back in the 1600s when he lived, but they figure if they measured his IQ, it was probably well over 200, that's incredible. I mean, I think Einstein was only like 160, okay? So, I mean, you know, that's like 3 or 4 points higher than mine. So that's, you know, pretty good. So going, yeah, I don't think so. Newton did a lot of things. And we're going to, in the next unit, we kick off the next unit on forces with Newton's laws of motion. So he did a lot of things. He did stuff with light. He did universal gravitation, which is exactly what I need to go through now. Now, this is Newton and the law happens every single time. Every single time. Drops. Every time. Every time. Law happens over and over again. Law of universal gravitation. Universal means it works anywhere in the universe, hence universal. Does it work on Mars? Yes. Does it work on Proxima Centauri, the first exoplanet closest to us in the Alpha Centauri star system? Yes. How do you know? You've never been there. Okay, moving on. It's universal. And we'll show you why it's universal in uno minuto. There, old angsty Billy. Okay, gravitation. Now the thing is about this, you know, I can teach this in forces, but we've learned about gravitational acceleration. We did that in the last topic of kinematics, universal gravitation, gravitational acceleration on Earth. So it kind of is a really good segue. Dean Kamen, anyone segues? Yeah. Yeah, that guy, okay? It's a good segue into the force unit. So I'm going to teach it now. It's going to be part of this unit, Unit 1, but it's our segueing into the next unit on forces. Because gravitation is a force. All right, now forces are measured in what's called, in the International System unit of force, called the Newton. Makes sense. I mean, look, he's the guy. He gets a unit named after him. I'm waiting for a unit named after me called the Gunroom. I'd be so wait. Okay? I'm going to have it one day. You watch. The Newton measures force. You know, if I told you that I have a 200-pound bag of flour, could you please lift this up and bring it upstairs for me, please? And you're going to go, 200 pounds? That's, hernia, no, can't do it, no, because you know it's a lot of weight. All right, so if I told you, though, I had a 10-pound bag of flour, you go, I can do that. So we have an idea of what a pound is in terms of how much force we have to apply to lift a pound. But now to Newton. So we've got to get familiar with the Newton. So the Newton, when it comes to pounds and newtons, 1 pound is equal to 4.45 newtons. So a pound isn't a lot. You can lift a pound, piece of cake. You just move a pound easy. And it takes 4.45 newtons to make a pound, so therefore newtons aren't very much. That's really kind of what we need to know right now. We'll get more into newtons in the next unit when we specifically go into forces. But for now, know that the Newton is the unit of attraction or repulsion force that's caused by gravity, which is actually an attractive force, not a repulsive force. But there are repulsive forces, but gravity is an attractive force. Okay, so gravity is going to be measured in newtons, a force of attraction. Newton came up with an equation. Actually, he came up with a proportion. Technically, it wasn't an equation yet. Before he died, he was waiting for it to become an equation, and he waited and he waited and he waited, and he died. All right, so how is it that Newton developed this law of universal gravity? Well, as the story goes, he had a pandemic himself, okay, not coronavirus, but the plague, yeah, nasty stuff. Back in England in the 1600s, later 1600s, and he was at Cambridge University, and they decided, well, they did know this, kept people away from each other, which social distancing, yes. So Newton had to go home from university. He was bored. He was sitting out in an apple orchard, And he was, sitting there and thinking and doing what Newton does, thinking. He was watching apples fall from trees. Supposedly, it goes hit him on the head, and he discovered, probably not, okay, probably not. But he was watching apples fall, and he went up, oh, he had an epiphany. And he said, oh, Mr. Johann Kepler came up with some planetary laws of motion. And so I could take my gravitation law from his laws of planetary motions and watching apples fall to the ground, and his epiphany came true. So what he did, he developed the following law from Kepler's laws of planetary motions and watching objects fall to the earth. So here's what he said. He said that the force, F for force, of gravity, G for gravity, is equal to some constant. So this is actually why I said earlier he didn't actually develop an equation, he knew a proportion. So what I'm going to do is take out the equation for now and put kind of as wiggly equals, meaning a proportional to. Again, kind of equal, but not exactly. Proportional to some constant. That was the stickler for him. We're going to call that constant big G. He didn't know a way of actually calculating big G. It's a universal gravitational constant. So let's write that down. Big G is the universal gravitational constant. Universal means it applies anywhere. And it's a constant. The number never changes due to attractive force, gravity. He did not have the instrumentation in the 1600s to come up with an experiment to get that value. So it took about 150 years later, a man by the name of Cavendish, the Cavendish Experiment. He had the instrumentation to do it, and he knew a way to do it, and he calculated what that G value is. Newton didn't know it. He was waiting, as I said earlier, waiting, and died. So, according to Newton, technically Newton didn't actually even have the G in there, because if he had the G in there, it wouldn't be an approximate, it would be a proportion, it would be an equation. So he said, though, that M, plain or peanut, M&M, mass 1, mass 2 divided by R squared, and then that can also be a D. Sometimes you'll see this R written as D squared. It means the distance between two objects. It doesn't mean radius. R stands for the distance between two objects, any two objects, how far away they are. So Newton knew that this force of attraction, gravity, was going to be directly proportional to the masses of the object. So if you double the mass of any object that are attracting each other, like the moon and the earth, then you would double the force of gravity. He also knew that distance was a huge playa. Playa on the bottom means it's an inverse proportion. So that means the farther away things get, the less gravity there is. You know that. There's less gravity the farther away you are from the earth. Okay? But it's an inverse square relationship. An inverse square relationship, meaning, see, it's an inverse. Inverse meaning because it's on the bottom, it's an inverse relationship. And squared, you can see there's a square. So what does that mean? That means this. That if two objects are 1 foot away from each other, they'd have a certain amount of gravity between them. If you take one of them and move it so it's 2 feet away, gravity goes down. They're farther apart. Does it go down by half? Because you went from 1 foot to 2 feet, you doubled it. The distance, does it go down by half? No. It goes down to 1/4 the original gravity, inverse square. So if we have an object and you move it 2 times as far, then the gravity goes down, inverse, goes down, square, to 1/4 the original. So that means distance is really important when it comes to gravity. Mass is important, but distance is even more important, much more important. All right, so this is what Newton developed. He said that there's an inverse square relationship with how far things apart and how much gravity they have between them. He said there's a direct relationship with how massive they are. So gravity is an attractive force. So if you want to become more attractive, eat a lot. Okay? Eat everything in sight. You will become more massive and you will become more attractive. Okay? All right? I'm talking gravity. don't fight it. It's physics. Okay, it is physics. It's true. True. Okay, now Cavendish comes along and determines what big G is. And that's what constants do. Constants in math make proportions into equations. There are a lot of constants in physics. And these constants are important because they make these proportions, these relationships into mathematical equations that we can solve for. So this value here, developed by Cavendish, is, all right, you ready? Here's the number. 6.67 times 10 to the negative 11th, and it does have units associated with it. They go with the units that are involved in here. Kilograms squared, because you're multiplying meters squared, and the force is measured in newtons. So it ends up being newtons meters squared over kilograms squared. Those are the units. I'm not going to write them down every time I do a problem. I just use this number, but those units are associated with that big G value. This is a universal gravitational constant. This value never changes. It's the same no matter where you are in the universe. What if you're on Mars? Yeah, okay, it works. How do you know? You don't know that. You don't know. It would, and here's how. When Cavendish did his experiment, you can look it up, read about it. It's actually kind of interesting. In undergraduate, I had to do the Cavendish experiment. And many undergraduates in physics do the Cavendish experiment. And it's like, whoa, this is so awesome. And you can determine this. You don't need the Earth. You don't need the Earth. It's just massive balls of lead on a torsion scale, torsion spring scale. And what they do is they will very slowly rotate toward each other. This has nothing to do with the Earth. Because remember, anything horizontally, gravity doesn't get involved. Gravity's like, I'm out, man. I'm out, not doing it. Up and down, yes, gravity. Horizontally, no gravity. So these two objects will move toward each other. It doesn't matter what the gravity is going down. In fact, it works the same on both. Those gravities go away, they cancel. You do that on Mars, these two things would attract each other the same. They're moving because their attraction for each other has nothing to do with the planet. Universal, people, universal. Okay? All right. So this value has nothing to do with Earth. Nothing. This value goes in there, works anywhere. Mass is not on the Earth. Mass is not on the Earth. I mean, math is not just exclusively something that happens on Earth. It happens everywhere. Mass is the amount of inertia something has. If you have 2 kilograms of mass here, you go to the moon, you have 2 kilograms of mass. Doesn't matter where you are. Distance this far is a meter. Now, maybe on a different planet, they might have a different unit that they use, but the equation ends up being the same. That meter distance here is the same on the Mars. If I go to Mars and get teleported, still the same distance. Irrelevant if I'm on Mars or not. So this has nothing to do with the Earth. This is universal. It would work anywhere. Okay, so there's the equation for it. Now let's have some fun with it. Let's have some fun with gravity. Yes. All right, now. Do you remember? No, you don't. I briefly mentioned it in an earlier video on kinematics, but there was an equation. No, I'm not going to get into that. Forget that. I'm going to tell you this. You can calculate your weight. Okay, I did a video on weight versus mass. Actually, I haven't showed you that one yet. I'm just babbling right now. Okay, here's another equation for you. You ready? So many videos, I don't remember who I've told what. It's a mess, I'm a mess. Force of weight is equal to mass times little g. Don't confuse little g and big G. Big G, universal gravitational constant, 6.67 times 10 to the negative 11th. Little g is the force of gravitational attraction on the planetary body you are on. If you're on Earth, near the surface, 9.8. If you're on the moon, 1.62. If you're on Mars, it's 3 point something something. So the little g is going to change. Big G does not, no matter where you are. All right, but let's put that over to the side. This is the equation to figure out how much you weigh, what your weight is. Force of weight. And there are a lot of F equations, a lot of them. We're going to be hitting you with all kinds of F equations. So far we have 2 already. F sub G, F sub W, that's weight. This is force of gravity, that's the force of weight. There's F sub F, the force of friction. There's F sub n, that's called normal force. There's F sub c, that's called centripetal force. I mean, pretty soon, after I give you all these F's, you're just going to go, F this. F this. Sorry. All right, moving on. So let's have some fun with this equation. All right, what do we got? Who wants to go? I need two volunteers who are sitting next to each other. Two volunteers sitting next to each other. Susie and Billy. It's always Billy. He's so angsty. And then he's not going to be in a good mood after this watch. Billy, okay, and Susie. Okay, so right next to each other. I know you can't see them at home, but trust me. Right next to each other, about 1 meter apart. Let's figure out the universal gravitational force between Billy and Susie using our universal gravitational law. What's interesting about this equation is it works not only anywhere, but for any two objects in the universe. Any two objects it works for. You can figure out the gravity between this marker and this rubber band. If you wanted to, you could do it. You could figure out between this piece of paper and this marker. You could figure out the gravity between any two objects, between Billy and Susie. Okay. Let's figure out the gravity between Billy and Susie. Let's see how much force of attraction. There is attraction there. There is Billy, Susie. I know Susie. I know. It's Billy, but you are attracted to him. Yes, you are. Yes, you can't fight it. It's physics. You can't fight it. You're attracted to Billy. Okay. Not in that way. I mean, but you. Never mind. Physics says they're attracted. Let's find out how. All right. F sub g equals big G. Now, this is big G. No, get out of there. Big G, 6.67 times 10 to the negative 11th. Now, the mass of Billy, we're going to give him 100 kilograms as a mass. It just makes the math easier. Susie, you're also 100 kilograms. No, I'm not. Susie, just work with me here, please. It just makes the math so much easier. Fine. Okay, thank you. Okay, so they both have a mass of 100, and they're 1 meter apart from each other. 1 meter apart. So I'll put a 1 in there and square it. This math is easy. I don't even need a calculator. Okay, 1 squared is 1. 100 times 100 is 10,000 times 6.67 times 10 to the negative 11th. So 10,000 is 1 to the 4th. I'm adding it to negative 11. So you remember what you do when you multiply exponents? Or add them, I said add it. You're multiplying it, you add them. So this will come out to be the force of gravity between Billy and Susie is going to be 6.67 times 10 to the negative 7th newtons. Or 0.123456667 newtons. Whoa, 1, 2, 3, 4, 5, 6, 7. You have to get into the 10 millionth of a newton. Now remember, newtons aren't very much. It takes 4.5 of them to equal a pound, which isn't very much. So whoa, that's like hardly anything. So Billy and Susie are not very attracted to each other. Told you. I know, all right, I know. But there is a little bit of attraction there. Not much, but there is a little bit of attraction between Billy and Susie. Okay? Billy wants to know how we can become more attractive to Susie. Billy, eat more. Eat a lot. Become more massive. Okay? You'll become more attractive to her. All right, now, that's not very much attraction. You and I don't have a lot of attraction for each other. These two things don't have a lot of attraction for each other. They're just not massive enough to have attraction. So if I drop them, they go straight down. They don't go and drop together because they laugh at each other. There's no attraction, hardly any attraction, but there's a little bit, but hardly any. Who wins? The Earth. The Earth wins. The Earth kicks the snot out of anything on it because it is so much more massive. So there is a lot of attraction between anything and the huge, massive Earth. Well, let's figure that out. Billy, you're up again. Me again? Oh, I want to be attractive to somebody. All right, let's figure this out between you and the Earth. But the Earth? The Earth is beautiful. Thank you. I've seen a lot of this country on the Earth, and it's nice. Stick with me. Fine. Okay, Billy, how much attraction is there between you and the Earth? Let's figure that out. So I need big G, 6.67 times 10 to the negative 11th. I need the mass of Billy, which we just said earlier was 100 kilograms, because we need Billy and the Earth. The mass of the Earth we need. Aww. Google it, or trust me, got it memorized. It is 5.97 times 10 to the 24th kilograms. That's a huge number. The Earth is massive. Now, divide that by how far away Billy is from the Earth. Maybe a few meters from the surface of the Earth? No, from the center of the Earth. These distances are measured from the centers of the two objects. So we need to know how far Billy is from the center of the Earth. Assuming that Billy is in Manchester, New Hampshire, which is close to sea level, here is the amount of distance to the center of the Earth. The radius. This is the radius of the Earth. Write it down. You're going to need this for many problems. The radius of the Earth. The radius of the Earth is 6,370,000 meters. Remember earlier I said you don't have to convert the kilometers into meters because you weren't using a physics equation. We're using a physics equation. You need MKS, kilograms, meters, and if we had seconds. So that is how many meters the radius of the Earth is. On average, it varies a little bit, but that's the average radius of the Earth, 6,370,000 kilometers. Figure out the gravitational force of attraction between Bill and the Earth. Do it now. Oh, I saw a predator. I saw a predator the other night, Friday night. I saw predators, awesome. And he said, get to the chopper. Do it, kill me, I'm here, kill me now. I'm bantering while you're calculating. Are you doing it? Calculate. A lot of big numbers here. You gotta be careful. A lot of big numbers. Be careful in the calculator. I got you though. You ready? You should get approximately 979 point yada, yada, yada newtons. Okay, you ready for this? Check it out. Let's figure out Billy's weight. How much does Billy weigh? FW, Billy's weight, is his mass, 100, times the gravitational acceleration near the surface of the Earth, which we are near the surface of the Earth at Manchester, 9.8. What do you get? 980. Boom. Boom. Same thing. Yeah, there's a little bit of rounding. Same thing. Yeah, same thing. Yes, Billy.
Why did you make me do all this calculating to get my weight? That's what it is, isn't it? It's my weight.
Yes, it is, Billy. This is how we get your weight.
But wait a minute, I'm confused. That's gravity. That's gravity.
Well, Billy, the force of gravity acting on you from the Earth is your weight. Your weight is the force of gravity of the Earth pulling on you. That's it. That's all it is. So gravity pulling on you from the Earth is going to be equal to your weight. So Billy weighs 980. Billy's force of gravity between him and the Earth, 980. That's because gravity is your weight. That's your force of the Earth pulling on you. Yes, Billy. So angsty. Yes, Billy.
Why did you make me go through all this when I could have done this? Do we have to use this?
Well, Billy, you have to use this. 1, if you're not on Earth. Okay. 2, if you're talking about the force of attraction between two objects, two markers. Or you and Susie, remember?
Yeah, I remember. She doesn't like me very much.
Shocker. I mean, yeah, it's too bad. So this works for any two objects anywhere in the universe. Universal gravitation. You will have one problem on your academic adventure using this equation. Okay? All right? Boom. Love it.